Okay, let's move on to a t-test. Now in the simplest terms, I just want you to remember T for 2. So a t-test is assessing for statistically significant differences between two groups. So implicit in that definition are the first two assumptions. Assumption number 1 is that we need an IV with 2 attributes. And these 2 attributes are going to be the 2 different groups. Assumption number 2 is that we have a DV, a dependent variable, for which you can calculate a mean, i.e. a dependent variable that is continuous. So let's look here at our fake data. I'm here using characteristic 1 as my IV, so I see 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. The ones in the 2's denote the 2 different groups. And I'm using characteristic 3 as my dependent variable. Here I can see it's a continuous variable, and so that will be my dependent variable. So I've met the first 2 assumptions. Let's think about assumption number 3. Assumption number 3 for an independent t-test would be independence of observations. By that I mean that the data would not be linked. If the data are linked, we would need to conduct a dependent t-test. An instance where data might be linked would be a pre-test and a post-test, and trying to compare for statistically significant differences between the 2 tests. But we're going to proceed as if this was an independent t-test. Assumption number 4 would be that there are no significant outliers. Let's see here. We can visually inspect that briefly, and I've also explored it by doing a box plot in another YouTube video. But let's sort these and just visually inspect them briefly. Let's expand the collection, expand the selection and continue. So I have everything from a 25 up here to a 36 down here. So everything looks pretty smooth. I'm pretty happy. So that would be the 4th assumption. The 5th assumption would be homogeneity of variances. Now we could do this in one of 2 ways. We could calculate the variance for each of our groups, and I showed you how to do that before using the var.s command. I'm happy to show you again. Or we could use the f-test in the Data Analysis Toolpak. So let me show you both ways quickly. First of all, I want to resort the data 1s and 2s. So the way I have the data now would be appropriate for processing in SPSS, but we're not working in SPSS, we're working in Excel. So I'm going to sort those. I will highlight all my 1s. My 1s stop right here. I'm going to copy and then paste. And then I'll do the same thing with my 2s. I'm going to copy and paste. I copy and paste. I'm going to call this group 1 and this group 2. So to calculate variance, I might do equals var.s. Oops, I did not want to do that. I'm going to undo that and go back here. This would be equals var.s, open parentheses, enter. I get 3.96. Here the same thing, equals var.s, open parentheses, and highlight these numbers. Hit enter. So I'm looking at 3.96 versus 6.5. As long as the variances are within a factor of 2, I'm pretty happy, and they are. Another way we could do this using the Data Analysis Toolpak, and I'm going to delete these numbers down here, would be to do the f-test. Now we need to remember that the f-test is sensitive to normality, and we have not tested specifically for normality, looking specifically at normality within each of these 2 groups, although we did assess for normality using the entire data set. We'll get to that in a minute. but I'll show you how to use the F-test. So I'm going to go to Data Analysis. I have F-test to sample for variances. I click OK. I'm going to delete that and delete this as well. So I click the button. Here we go. There's that. And then I'm going to look at group 2. Okay. Yes, I have labels in the first row, and we'll paste this in a new worksheet. I click OK. So in the F-test, we want to not reject the null, and let's set the alpha at 0.05. So here we see our p-value right here, 0.12. So 0.12 is greater than 0.05. We accept the null, which is what we wanted. If we reject the null, we would be saying that the variances are unequal. I can also see here that my F value is greater than my F critical, which is what you want when you are interpreting the F-test. Let's go back to our sheet number 1 and proceed. The next thing we might want to do is look for normality. Again, we assess normality for the entire data set, but when we're doing a t-test, we would want to ensure that each individual group has a normal distribution. I'm not going to do a histogram because histograms are very difficult to generate with sample sizes of 20, 25, which is what we have in these two subgroups. What I will do is look at skewness and kurtosis briefly. This is equal to skew, and I'm going to select all these numbers. Hit enter. So it's 0.87. We have a positive skew. That is somewhat close to 0, but it is different from 0. Remember, 0 would be a characteristic of a normal distribution. Here, 1.96. So I'm working with pretty peaked data. Again, I can't exactly assess if this is a statistically significant departure from normality. The value we would get if we were working with the normal data set would be 0. And we can't because we don't have that extra value, that extra statistic that SPSS calculates for us, which is standard error. But I think that it is maybe eyebrow raising, given a 1.96, that likely this is a very peaked data set. Let's repeat that. Let's look at our skew over here in group 2. I hit enter, 0.05, that's really good. Likely it's a symmetrical data set. Equals curt. For kurtosis, I'd expect a positive value here. It is. It's positive, which means it's somewhat peaked, but it's less peaked than this group 1. Do I feel comfortable proceeding with normality? Generally speaking, yes. I think that we have somewhat sufficiently met that assumption. Again, here in Excel, we don't have access to computing Shapiro-Wilk very readily, and so we're going to use our best intuition, or what I might call informed intuition. So I'm feeling somewhat comfortable with the normality assumption. So we've met all 6 assumptions. We have an IV with 2 attributes. We have a DV that's continuous. We have independence of observations for our independent t-test. No significant outliers. There's homogeneity of variances, and the DV is somewhat normally distributed. So let's go on and run our t-test. I'm going to delete these numbers down there so we don't get confused. Okay, let's go back up to data analysis. And here, t-test. We would select the paired 2 sample for means if we were doing a dependent t-test. If we had unequal variances, we would accept the t-test 2 sample assuming unequal variances. We're going to do the t-test 2 sample assuming equal variances. and I click OK. So let's look here. I need to delete that. Here's my group 1. I'm going to delete this. Here's my group 2. Hypothesized mean difference would be 0. That would be saying that I think that the null would be that the means are the same. Did I include labels? Let's see here. No, I did not include labels, so I need to uncheck that box, and I'll put it in a new worksheet. So let's click OK. Okay, and let's adjust this so it's easier to read. I see here that the mean for variable 1 is 29.8, the mean for variable 2 is 29.9. Those are extremely close. I wouldn't expect that those would be statistically different. Here's my variance again. I have 22 observations in this group, 28 for a total sample size of 50. Let's move down here. The p-value doing a one-tailed t-test would be 0.43, and for a two-tailed would be 0.86. I would probably go with the two-tailed. The two-tailed is going to be a bit more conservative than the one-tailed. Doing a one-tailed test would increase your power. But I would do a two-tailed unless I had a strong hunch that there was a specific direction to the difference in the means. But I didn't, so I'll look at that two-tailed. With a p-value of 0.86, I would accept the null being that there is no difference between the means of the two groups. So there we go. Thank you for hanging with me. Bye-bye.